So we know that interfaces on Earth are important areas of biology and biogeochemistry, but we also know that it is very challenging to capture these processes in models. So for example, the air-sea interface, these are smaller scale processes that happen that are not adequately captured in models that we have of Earth. So the question is, what are some of the challenges in capturing interface processes on Earth and in ocean across our solar system, and what could we do to improve those modeling exercises?
Oh, what a good question. So the first question was, most of you have probably seen backscattering from particles from, say, the Argo floats. I talked about that during my talk, but it doesn't really give us much about the particle composition. So it's something's there and it's scattering light back, and we know it's enhanced, right? But, you know, we're getting better models, and then certainly we're getting better technology. So in the simple sense, we can do some things like a backscattering ratio, which can tell us the sense of the index of refraction, which is kind of nice because is it a bag of water? And if it's a bag of water, then that might be an indicator of life, right? So if it has an index of refraction that's closer to water itself, then it suggests that it's something maybe more living than if it's a hard particle that suggests maybe it's more something that's like a sediment or a mineral. And those things we can do optically. We have the technology to get a volume scattering function, and that's the scattering of light in multiple angles in the water. And from that our modelers are getting better at the decomposition of that into things from air-filled bubbles to like hard particles like calcite to watery particles like phytoplankton. So the technology on Earth, while there's still a lot of uncertainty in measurements of models, I think it's progressing pretty rapidly where we could get better sense of the particle composition just with backscattering. Was that your question, Laura? I know that was the first question. Wanyang, do you?
Yeah, I just totally agree with what you just mentioned. Yes, I think we definitely are heading to the right direction. Our model now can account for more and more processes. But I think currently most of the challenge that I see in most of the GCM or kind of LES simulations are I think there are two major challenges there. One is that no matter it's a water ice interface or at the seafloor, we treat the interfaces as a solid kind of 0-1 type of transition. There's no like transition, but in fact, for example, in Enceladus, if the ice is in contact with the ocean, then over time it will develop this mushy zone. And recently there are papers getting out, and they talk about how these dynamics may change the dissipation rate and also change the tracer exchange processes. So I think that part is still yet to be well represented in most of the models, and because it's difficult, it involves fluids and transmitted through a porous media, and we need to have those specific model or algorithm to calculate all these processes out, and how the matters and tracers are exchanged between the liquid phase and the solid phase. And the second challenge that I feel is very another obvious challenges that I see is that the tracer transport. So as you mentioned, there are these gas phase and solid phase that is dissolved in the water. Now, in most of the models, we can add in passive tracers very easily. We can allow it to transmit and so on, but they are not allowed to have their own dynamics. So imagine that if you trace a particle, it doesn't follow the same path of a dissolved kind of tracer composition, like dissolved sodium or something. So they are different. And because they are a real part, they will follow different dynamics and follow different paths, and they have different transport timescale. And current models don't have that process built in. So I feel that in order to understand this process better, we really need to improve in this point.
Thank you. That was awesome. Is there, oh my gosh, why does it, okay. Is there anyone from the panel that wants to add anything before we move to our next question? And we have a bunch of questions lined up, so we're gonna make sure to try to keep each question to about 2 minutes. Okay, hearing nothing. Ashley, go for it.
Okay, thank you. So for our next question, we're going to call up Allison, Dawn, and Thorsten. And the question is it sufficient to study the ocean under a currently melting Arctic ice, or should the research focus more on processes during, say, the Snowball Earth period of history?
I think I'm here and I'm unmuted, so I'm waiting. Is Jackie get into, or any other panel member?
I think I'm here.
And there's Thorsten. All right, lady and gentleman, go for it.
Who wants to start?
So I'm just going to say that you got to start.
Well, I can.
Yeah, go ahead.
I can start, I guess.
All right, go Allison.
So I think that maybe the real answer is not either or. I think that really I think that there's a lot that we can learn. The studying Snowball Earth is done through looking back in history and looking at some seafloor geology, but there's so much that we can't know about what things were really like during Snowball Earth. But I think that having that perspective and taking what we have on Earth today and being able to hind cast it, I think is really important. We have a lot of life on Earth today, though, that was the microbial world was survived through Snowball Earth, and I think that there's a lot to learn probably about what processes really persisted through the Snowball Earth time. So there are some working under melting Arctic, working under ice shelves in Antarctica, in subglacial lakes, in ice-covered areas, and understanding the processes of life and how life really impacts the biogeochemical signatures that we can see, I think is probably a good way forward.
My first thought was when we talk about Arctic melting ice, is it the ice, is it the ice shelf, the ice sheet, or the sea ice? Because they are very, different system. And as Allison said, I think the subglacial lakes in especially in Antarctica could be a good analog. With regard to sea ice, the one question I always have is when it comes to using the Arctic Ocean as an analog for the icy moons is, there is no light on, in the ocean of the moons. There's no biochemistry in this regard or photosynthesis. So, and I'm wondering, and I asked this question in our panel, whether the models are, can actually switch off light, and you can adequately model, the chemistry of the ocean, under the melting Arctic ice. I don't know.
Yeah, I'll chime in on that too. From the Snowball Earth perspective, I thought long and hard about that. And I think what we don't understand from Snowball Earth are the processes that dominated when we froze Earth, when Earth's oceans were frozen. And we haven't really thought very hard about where to look on contemporary Earth to understand the processes that were happening on Snowball Earth. There are a few places where the ocean is freezing and there isn't any snow. And so you actually, McMurdo Ice Shelf in Antarctica is a good example. And you have marine ice from frozen ocean under, 100 meters of the stuff or something. And it's actually interacting with the seafloor very interestingly. You get rafts of seafloor material that are incorporated into that ice shelf. And because it's adding at the bottom, at the surface, sponges come out, things like that. And if you think about that as a process applied globally in Snowball Earth, there should be some novel implications for the deep sea sediments that are of that age. And I've just always wondered whether anybody has chased that around. And then to obviously take that to Europa, and that's just an exchange like we're expecting on Europa, where we add material at the bottom, and then we have some overturning of the ice shell, and then hopefully that material sees the surface, and similarly, on Europa, the surface sees the ocean interface. But it's that one where the ocean material ends up at the surface. And I'm not talking about plumes, I'm talking about advecting material. So that's the one that's always baffled me, and I think is worthy of work. Just because we don't have it operated, because Snowball Earth isn't a reason to not study Snowball Earth processes that are out there right now.
Thank you. All right. Just so everybody knows, we're taking really good notes about all the answers that you're giving. So speak freely, but just know that everything is we're going to synthesize it, because these are great points that we hope also to incorporate into white paper. Okay, so the next question that I have, I'm going to pull Michael, since he's already on stage. But I'd like also to call Mary and Paula on stage. And the question is a pretty simple one, but it's one that we want to think about. And I think it's really synthesizes the purpose of why we're here. And the question is, what would planetary scientists be looking specifically from Earth oceanographers, and vice versa? What do you think should Earth oceanographers be the best interest to collaborate with planetary scientists and planetary oceanographers?
You seem to be muted, Paula.
Thing.
Maybe Mary can take it.
Yep, Mary, why don't you hit it off while Paula gets the. Maybe you need to refresh, Paula. Just hit Control R.
Yeah, I actually missed the full question because I had to refresh. Can you actually repeat it?
Happy to. The question is, what would planetary scientists be looking for from Earth's oceanographers, and vice versa? What could Earth's oceanographers be leveraging on from planetary scientists studying other ocean worlds?
Well, I think that one is a little clearer than others because we've been doing it for longer, which is, basing the studies of other planets in our solar system, and indeed even exoplanets, so planets that orbit other stars besides our own. What we know about how planets operate are completely based on what we understand about Earth, with a little extra information as we study the planets closest to us. So just like we learn about volcanism on other planets by understanding volcanism on Earth, or planetary differentiation by understanding what happened here on our own planet, the way our oceans function and the sort of, whether it be circulation or or geochemical cycling or whatever it is, our knowledge begins with what we understand on Earth. I would say in terms of what comes back to the Earth community, is something I'll say that Exoplanets has done for the planetary community, which is, you know, when you start out with a sample size of 1, which is of course also why we really want to find life somewhere else, everything you know about that topic is based on that one example. So what we know about solar systems and based on our own solar system. And then when exoplanets started being discovered, we suddenly discovered that solar system, that first of all, the distribution of planets are very different than what we see in our own solar system. Their relationship to their stars and how they function is likely very different. And everything that we thought we understood about a solar system that was based on our own kind of got blown out of the water, and all the various models we had for how planets are formed and how they position themselves. If you try to apply those similar principles to other solar system, it just doesn't work. And so it has sent our planetary scientists back to the drawing board to understand. It's almost as if their models were overfitted to the single example. And so what I would say is that as we begin to explore oceans on other planets, some of the things that we understand about our own oceans may be challenged because they don't function when you start applying the models that we use on Earth to other systems. And we have to go back and because the models have been overfitted. And so it will broaden our understanding in general about how systems work once we start getting more examples. So I think, to me, this whole concept of comparative oceanography is very important and is going to feed both directions. Take it away, somebody else.
Paula, are you back online?
Oh, Paula, your audio still is cutting in and out. Michael, do you wanna anything?
Sure.
I'll challenge you also, considering your background. Maybe you want to comment also on origin of life.
Sure. So I think Don gave a great example of this interplay. So he was talking about Snowball Earth and how there are processes that he feels that were important in Snowball Earth that you can observe today here on our current Earth. But we can see a snowball planet, which is Europa, to the best of our knowledge, and others. So what I think, and to build on what Mary said and what Don said, I think what planetary science can bring to oceanography, a set of conditions that are radically different from current oceanographic conditions, some of which may have analogs back to earlier conditions on the Earth, and some of which are just completely unusual, and will push our understanding of how the processes on Earth operate into realms where maybe our models break down. Maybe they work fine, I don't know. But it does provide us with a much broader laboratory, a larger set of samples, n greater than 1, as Mary said, that will let us understand how things operate. As far as origin of life goes, again, there are places in the solar system, ocean worlds like Europa again, and maybe Titan, where there is possibly chemistry going on that is similar to what we think the kind of chemistry that went on the early Earth that led to life may be happening. We generally tend to think of a model of the European Ocean as having thermal inputs at the bottom and ice at the top, and you have to have some kind of exchange, particularly between what's on the surface of the ice and the ocean beneath it, and that builds on what we think we understand about some ways in which you could have made life on the Earth. Titan has a incredibly charismatic organic chemistry based on its atmosphere and the radiation environment, which also can tell us things about origin of life on Earth. Whether either of these systems could generate life like that on Earth or unlike that on Earth, we don't have any clue, which is why we really should go there and poke around and find out.
Leo. Can you hear us?
I can. Can you hear me now?
Yay!
Yay!
Better. Sorry. Welcome to where I'm sitting. I'll be brief since we've been on this question a while, but I thank Michael and Mary. I wouldn't say anything any differently, but I would say to everybody who's out there and thinking about this, to everybody who joined today, we spent an inordinate amount of time at NASA thinking about the interdisciplinary science and comparative oceanography, like Michael and Mary just identified. And we were talking at the breakout on the Rogue table about how it's not just research that's relevant, it's technology that's relevant, it's modeling that's relevant. I sat in so many meetings in 18 years at NASA headquarters where people would say, if we only had a sensor that measured X, in water, that'd be fantastic. Meanwhile, the Office of Naval Research had been funding that kind of work for decades, right? And so the opportunities to sort of bring those communities together when it happens and it's close is going to be real. And I want the Earth scientists and the planetary science, my hope is that they start realizing they're studying a lot of the same problems, right? And that there's a lot of relevance, and that it is, anything happening planetary wise is relevant to the Earth and the Earth system, potentially climate change and solutions. Anything we're seeing in the Earth and climate change is potentially extremely relevant on other bodies. So I'm really hopeful for the future. I think it's going to be an exciting time. And we were talking about maybe a union session coming up at AGU, where we start to showcase some of the science that we're doing that's collaborative and get these communities together.
Thank you to our three panelists. And we're going to go to the next question, which Ashley is going to take away.
Yes, thank you so much. That was great. So for the next question, we're going to call up Ved and Tori. And the question is, how is pH or anything measured in a liquid ocean under ice or at the distance of Saturn and beyond?
Tori, would you like to take it away? Or?
Yeah, I think the simple answer is not easily. So this actually has been done in one case and not directly measured, but at least constrained. And that case is for Enceladus, where the dynamics of the moon actually provide us with samples that we can fly through and access. And so the way that the constraint has been levied in Enceladus is to look separately at the abundance of carbon dioxide and of carbonate species anions. And do the same kind of carbonate speciation calculation that we do on Earth. So if you have those species, if you have the abundance of those species constrained, you can then constrain what pH was required to give you that distribution. So constrained, not measured. And that's because there are a lot of not well understood processes that may act on the ocean material as it's ejected into space, may serve to fractionate it, may not serve to fractionate it. And so I don't think that we can necessarily look at those things as a direct sampling of ocean chemistry, but a process sampling of ocean chemistry. And that's something that we're going to have to face, a challenge we'll have to face on any of these worlds, is understanding when the stuff that you're interested in, the ocean water that you're interested in, is beneath tens of kilometers of ice. The chances that something has happened to it and modified it on its way from its point of origin to the point at which you sample it is high. And so a lot of the research that needs to be done in regards to life detection, for example, as an extension of the pH question, is exactly that. How do we factor in those processes of modification, and how do we use that to inform the way that we search for whatever it is that we're interested in measuring these places?
Yeah, I think I couldn't have said it any better than Tori did, which is, my specialty is remote sensing. These are the definition of the most remote systems you could get to. In our subsection for the white paper, we wrote about the active and passive remote sensing technologies that could be applied to this. There are some examples where the remoteness is not so bad because there are things being spewed up into orbit that you could measure remotely. But I think we came to the determination you would need a combination of in situ measurements as well as remote sensing technologies to get there. And I like the approach of taking, my background's in physics, where you never really get exactly the answer you're looking for, but you can constrain the system incrementally down to a very narrow margin of error. And I think that's the approach that might be needed for these really challenging environments, because the lander may fail. You may be left only with orbital measurements or vice versa. And that's something that you have to be prepared for. And you want to get some science result out of these missions.
Super. Thank you. I love how you guys just address everything, and it's not easy. Absolutely. Thank you. Our next question, we're going to call Jeff, Mike, and Anna up to the stage because it's a complex question. It talks about diversity in the ocean. So on Earth's oceans, diversity has latitudinal gradients, and those are based on light, on ocean circulation, and other factors. So what gradients should we expect in ocean worlds? And this has to be ties back to what kind of current may we expect in one of those icy moons that may influence how communities organize, how food might be distributed, and should we be expecting, top and bottom, competition for substrates, or what the heck is going on?
I actually missed most of the question. You were cutting out. I couldn't actually hear.
Sorry. Let me.
Same here, Laura.
Is this better? Can you hear me now?
Yep.
Okay, I apologize. So the question has to do with diversity in the ocean. In our ocean, in Earth's ocean, diversity is based on latitudinal gradients due to ocean circulation, light, heat, and other things. So what gradients in terms of assuming that there is life, should we expect in ocean worlds? What kind of currents are we expecting, and could those influence how communities organize in those icy moons? And should we expect, the top of the eye, the under ice, and the floor of the moons to be packed with, microbes? And could there be a competition for substrates? This is assuming that we do indeed have potentially life.
I guess I'll take a shot at it. It's a fairly complex question, and I guess the simple answer is yes. But I think you need to think about energy gradients, and really what I think on Earth we know that the life follows the energy. So I think we don't know what the sources of potential chemosynthetic energy are on other ocean worlds, and I think it's going to require a lot of modeling effort to what is possible at the interfaces, the water-ice interface, what's possible at the seafloor, the water-rock interface, and then factor into all of that potential currents, which may be very different than we see on Earth. So really important question. I don't know. I guess the expectation is also how complex are the ecosystems? So are we limited to primary producers, or are there other more complex ecosystems that are existing in these environments? I'll let somebody else comment.
Anna, do you want to go next, or you want me to take a shot?
Why don't you? This is a little bit outside of my expertise, or maybe a lot outside of my expertise.
All right. Well, I think Jeff touched upon some important points. Life on this planet is a high energy, high biomass system, and the amount of energy available to support life, to the best of my knowledge, and Tori's a better person to respond to this, is on the order of about 5 to 6 orders of magnitude lower than we have for life on this planet. And that source of energy is most likely going to be fairly concentrated into specific places like a vent or something like that. And there are a lot of important ramifications of that. So it seems likely to me that the amount of biomass that's supported is going to be very small compared to Earth. And it also seems likely to me that the ability of that life to adapt and to spread is going to be very limited. What we understand on Earth is that that diversity, evolution, is driven, at least in part, by the product of a speciation rate and the number of individuals. And so we expect for these other icy worlds for that equation to yield very, very different numbers than on Earth. So we expect probably that the speciation rate is going to be slower per individual, because there are a number of sources of speciation or mutation in genetic material that are not present, such as UV light. And we also would expect, because of the energetic differences between these planets, that the number of individuals is very, very small. And so the random probability of mutation and the rate of speciation is going to be very, very low. So I would expect the diversity to be extremely low, and thus also the evolution of that life form, if it exists, to be very slow. So I'm not sure that we would expect life on another one of these planets to evolve and adapt to changes in the environment in any manner similar to that on Earth. Anna, do you want to add to that?
Sure. I'll just add something that also sort of came out of the breakout group I was in, is this idea that we need to be able to make measurements kind of across areas, that just taking one single measurement is not going to tell us everything. And so this idea of how do you make measurements across different gradients, which I think is applicable here. And the idea that also, like, we've not solved all of this in our own ocean. So coming up with ways to really test this in our own ocean first can really illuminate the ways that we would do it. But I think this idea of, just one measurement in one location is not going to tell us everything. And that was sort of an idea that we really talked a lot about in my own breakout group.
Thank you so much. Ashley, take it away with the next question.
Sorry, I was struggling to turn off the mic button. So thank you so much. That was great. So for our next question, we're going to call up Chris and Jackie. And for the question, it is, how often might eruptions on icy moons happen, and how does this affect our ability to collect data from them?
I'm gonna.
I'll add the link back, and I'm sorry, I'm hijacking the question, and please forgive me, but I'll add the link back to our own Earth, which would be how do those eruptions might relate to what we know about volcanoes or underwater volcanoes on Earth. Sorry about hijacking the question.
No, that's fine, because since I don't really study planetary systems, going to the eruption part, I was going to let Chris answer some of the timing of that, but the fact that we have them hydrothermal vents and chemosynthetic organisms and life there indicates that the potential mechanism that would happen on a planetary system at the rock-water interface. So that kind of feeds into biodiversity and potential for life issues, and also potential to that circulation question, because I think the idea is it makes convective cells on planetary systems such as Europa. But for the other part of it, Chris, I'd let you take it from there as far as potential numbers of volcanic eruptions.
Thank you, Jackie. What a wonderful question. It's very imaginative. Let me think how I'd actually, while I'm thinking, Laura or Ashley, can you just repeat the full question again? I was accepting my camera and you went blank on me a little bit mid-sentence.
No problem. So the question was, how often might eruptions on icy moons happen, and how does that affect our ability to collect data from them?
Okay, so a really simple answer is we have no idea, right? We know we have continuous volcanic activity on Earth's seafloor, but in the current Earth that we're living on today, that's because we have plate tectonics of a certain kind that we have today. There's no requirement that happens on any other planets. In terms of how much heat they trapped at the start and how much they're releasing, we don't kind of know how that's happening. We also know, if we go back in Earth history, that we can't actually trace plate tectonics like we have today more than about halfway back through the history of our own planet, and that things used to be different. But there does always seem to have been some kind of volcanism, and there does always seem to have been some kind of hydrothermal activity as far back as our geologic record goes on our own planet. And then if we do look at other places in our solar system, we definitely know that volcanoes happen, right? We can see massive fossil volcanoes on Mars that date from the same period of when there was water on Mars. And we can see if we go out to the outer planets, if we look at Jupiter, then we know that there's volcanic activity happening on Io. In fact, that was the first place I was interested as a seafloor geologist. The first time I learned about Europa was by accident, because I went to a session at AGU talking about the volcanoes on Io, and then I was just too polite sitting in the middle of the road to get up and walk out when people started talking about Europa instead. But the logic applies that the reason that Io is so volcanically active is because of this tidal heating that happens when you have multiple moons the size of our moon all rotating one around another. And then with a large planet as well, that's basically, it's the frictional heating that keeps things molten on the inside. And so that's why Io is so volcanically active. So a simple assumption then might be, well, then if Io can have volcanoes, then why couldn't Europa have volcanoes? Because it's not that much further out as well. It turns out that it actually gets more complicated than that, because where the tidal heating happens doesn't necessarily have just a solid rocky layer. So any tidal heating has to happen in the rocky layer, and that's why you get volcanoes. On Europa, the question becomes, does the tidal heating happen in the rocky layer, or does it happen in the ice shell that's flexing up and down? Because the outside of Europa is going up and down, I think, something like 30 meters per orbit of a few days. So the ground's going up and down all the time on Europa if you were a lander. And then there's the ocean in between, which might just be acting like a giant shock absorber, like when you're driving a car down the road. You have suspension for a reason, and it's because that's where the energy is getting dissipated. So those are all open questions that we have to try and bear in mind of where things might be happening. So when it comes to thinking about life, then it's, well, where's the energy? Is most of the energy in the ice, or is it in the ocean or in the rocks? And the encouraging news is, even if there isn't a lot of volcanic activity, one of the things we know from studying Earth's hydrogeology on ridge flanks, for example, is that we know that on frozen moons, like our own Earth's moon, we know that if the pressure differential, because of topography, if you put an ocean as thick as on Enceladus or Europa on Earth's moon, water would start to flow down under the rocks in some places and come out in others, and you would get chemical reactions. So, you could pour a big bucket of water on our moon and turn it into a habitable environment, chances are, because things would be out of chemical equilibrium. So it just becomes like a fascinating open-ended, it's such a short question and such a long answer, because all the different ways that you could combine rocks and water at the seafloor in lots of different ways can give you a whole variety of different kinds of chemical energy that could be available for life. I should probably stop there while there's still any oxygen left in the room.
That was fantastic, and I wish we had, again, I wish we were in person and had more time. And we are saving all the questions. So as you probably see the clock, we're almost out of time. We're going to squeeze in one last question, but we're saving all of the questions that we didn't get to. And these are absolutely fascinating. And so we'll be looking to maybe providing some answers to those from our panelists, who have been absolutely fantastic. So for our last question, we're going to call Allison back on stage, Mike and Tori, because we're going to ask a biosignature question, and you might recognize this as one of the topics of one of our plenaries. And so the question is, how can we characterize biosignatures and biochemistry in ocean worlds?
Who wants to go first?
Go, Tori.
All right, I'll have a quick go at it. I think the very first thing that we need to do is walk the line between, taking a good look at the example of life that we do know, and not letting ourselves be too constrained by what we see in front of us. So that's part one. Think a little bit more broadly about what constitutes evidence for life. And then I think the second important thing that we need to do is free ourselves a little bit of our intuition for what an inhabited world looks like. As Mike said earlier, we live in a place that is absolutely replete with energy and resources, and it gives us a very particular view of what we can expect to see when we find an inhabited planet. I think that it might look very different in a place where resource availability is much lower. And armed with those two things, I think that we can be careful about the way we select the instruments and the kinds of observing strategy that we would use to look for life elsewhere.
Allison, do you want to go next? Or do you want me to take a shot?
Sure, I'll go. I think I resonate there with what Tori said, and I think that looking not only for the things that are life, but also looking for the byproducts of life is a key thing, and we can do that both with chemical and physical measurements, and developing these types of technologies. We do this on Earth fairly well, and so I think by looking and taking the technologies that we have on Earth, but we do this on Earth very well, but we aren't normally, we normally come to Earth as oceanographers on Earth, we know that there's life there, so we sort of, we don't, you have to sort of invert the question a little bit. And I think we can actually learn a lot more about how life on Earth is impacting the ocean, the sediments that we see. But I think looking both for the life forms, but really focusing on how those life forms are impacting the chemistry that we see. So, for example, the organic molecules that are produced and how long they persist in different in ices and in sediments, I think is an important thing. And then thinking about how we can detect those, especially if I'm thinking of in situ types of missions. So that's my answer.
All right, I guess the last bit that I would add to this, and I was thinking about this prior to the meeting, is you know, on Earth you can go to pretty much any place in the ocean and you can detect a signature of life. And in part that's because there's so much life here, and in part because life produces refractory compounds that can persist for hundreds to millions of years. But the question I was thinking about when I was before the meeting was, if we go to another one of these planets, do we have to actually find the life, or can we just look for its signature in the bulk water? And my thoughts are leading toward the former. And one of the points that Tori made that was very interesting in his videoed presentation was that, and Tori, correct me on the numbers, but if you look at the rate of processes on this Earth, all of the dissolved organic carbon in our ocean is consumable, I think, on the order of 100 years. Is that right? And all the DIC on the order of 1,000. Was that correct?
Yeah, of course it differs compound to compound, but I think if you think of it as a bulk average, it was something along those lines, maybe a dozen years for the DOC.
Right, and then the water content of this planet is minuscule per volume of planet compared to some of these other worlds. And so, and of course, because the energy flow in these other icy worlds is so low compared to Earth, it seems likely to me that the biological signature in the dissolved phase that is uniformly distributed across these oceans is going to be so incredibly small that it may mean that we have to actually find the life itself in order to detect it. It may just be very difficult to find that signature in the bulk water. And Tori, correct me again if I'm wrong, but the rough calculations on the optimistic side for processing of organic molecules on these other planets is on the order of 1 billion years for a single turnover. So it's very, very slow. Is that right, Tori?
Yeah, I think the key feature is that it's much lower. We have very little constraint on what the resource fluxes on these worlds might be, and so any calculation has to be taken with that in mind. Almost certainly the availability of resources is less than it is on a planet bathed in light. And so the take home is cycling of carbon or any other element is going to unfold over much longer timescales than we're used to here.
Can I add one thing too? I think that if we think about some of the places where, so in a low energy system, we may also still have concentrate, life may not be uniformly distributed. So maybe that there's the possibility that life could be, let's say, at the ocean ice interface where we have maybe something like the equivalent of gnats that we see on Earth today. Maybe the products of life then would be easier to find.
All right, thank you. We are past our time. Ashley?
Yes, thank you so much. That was really great, and what a way to end the session. It was very informative, so thank you so much. As Laura mentioned, we wish that we could take more time today, but unfortunately, that's all we have time for. But we are saving these questions, and we will be answering them. So as a reminder, the first draft for the Oceans Across the Solar System white paper is on the OCB website, and we will be looking for community feedback starting on Monday. So definitely take a chance to look at that if you haven't already. And we also just wanted to thank everybody so much for taking the time to join our Ocean World session today. And a special thank you, of course, to our absolutely incredible panelists and speakers for all their hard work, and also to Heather and May for organizing this. And then also to everyone that joined us today, we really appreciate your interest, your contribution, enthusiasm, and willingness to participate in the session. And don't forget to check out the agenda for the other exciting sessions going on today. Thank you so much, everyone.